Professor, I had a quick question.
Yes, what's that?
Hey, do you know if they're gonna have an option for the online lab for the next version of this course, or is it only because I remember I sent you an email and you told me
Hmm.
to email you a little bit later. I was gonna shoot you the email, but I have you right here. I might as well
Yeah.
just ask if you knew.
The last I checked, we had one slated that might be made into online test. I'm actually still trying to get a entirely different course made. Let me check on it. I should know the answer by tomorrow morning, and I can send out an email let you know about that. But yeah, I'll double check. But last I heard, we had one in the pipe. It was just a matter of whether we got enough enrollment. So I'll
Okay.
check. I mean, I know people started enrolling in it now. Did you see one listed as being offered in the fall?
I was trying to see out last time when I sent you that email, I had checked and I didn't see anything, but I
Yeah,
haven't checked since. I was gonna wait for an update from you, but
gotcha.
I'll check again today after the class is over.
No problem. I'm gonna check right now. Well, actually, I ain't got time to check now, but I might check if we take a break. So,
All
all
right, thank you.
right, no problem. Thanks, David. All right, I guess it's time to go ahead and get started, everyone. So what I mentioned to you guys that we're doing is I'm trying to knock out a fraction of chapter 14 and a fraction of chapter 15 today. And you're losing a little bit of information in that normally I go through the whole chapter, but to be honest with you, the stuff I'm going through is what's most critical. You have a certain amount of stuff you're going to learn about harmonic motion because you can't really understand wave motion until you understand harmonic motion. And not only that, harmonic motion appears over and over and over again in a lot of different guises. For instance, as you'll see in this chapter, if you're talking about harmonic motion, which is basically supposed to be, a mass on a spring, obviously that's harmonic motion. But it turns out you can also uh, hang something from a piece of ribbon and then give the little ribbon a twist, or the piece of thing that you're hanging from the ribbon just a slight twist, and then the thing will wiggle back and forth in simple harmonic motion. uh, you can do that with various other things as well, but a pendulum, for instance, is another case that behaves like a simple harmonic oscillator, at least with small amplitudes. So if the pendulum's going back and forth like this, if the angles, between 1 degree and let's say 20 degrees is actually surprisingly accurate even at 20 degrees, then that's a small angle approximation and you end up getting the equivalent of a harmonic oscillator. And you'll see there's a bunch of different examples in this chapter alone. So that's how important simple harmonic motion is. But it even goes beyond that. For instance, simple harmonic motion is exactly the equation that we end up solving when we set up an AC circuit that includes, in this case, it's actually possibly a damped harmonic oscillator instead of just a simple harmonic oscillator. But when you set up an AC circuit that has a resistance, a inductance, and a capacitance in it, the equation that you solve there from Kirchhoff's loop rule is exactly the same as the equation for the damped harmonic oscillator. So what your goal is upon leaving this course from this chapter is being able to recognize the differential equation that is reminiscent of simple harmonic motion, and recognize the equation that we call a wave equation, and figure out how to know exactly what the solution is in those types of problems. And we're going to show you some examples of that. So let's go ahead and get started. Anybody have any questions before we get rolling? All right, well, we're starting with chapter 14, and chapter 14 is just called Oscillations. And oscillations, actually, I remember when I first ran across this word when I was I think it was my first semester out of high school. Remember I told you I was a really, really horrible student as in grade school. I didn't straighten up till about till my senior year of high school, really. So I was way behind. I hadn't read any books. I had no real appreciable vocabulary or anything. So the word oscillation I thought was oscillation or something weird like that, and it was just something odd. And then I realized the couple months ago I was in Taylor Dewitt Center, and I say elderly lady, a slightly older than me lady, just says, "What do you think about this oscillating fan?" And I realized, it's probably pretty normal. Most people hadn't heard of that. So oscillation just means something where it's repeating itself in motion. So it could be something swinging back and forth like this. Could be, in some sense, something that would be swinging all around in a circular motion, as we'll see in chapter 14. That's sort of like an oscillation, or at least you can treat it like an oscillation. So neat stuff like that. But we're going to go ahead on, and as always, you should always read and try to take a poke at your chapter opening question as done here. But I want to get on first with talking about Hooke's law and the oscillation of a spring. So I'm going to go ahead and share my screen with you guys, and we'll discuss this. So let's share my iPad screen. So it's critical to understand that Hooke's law has a negative in it, and it's more critical to make sure you understand exactly why it has a negative in it, and specifically what the importance of that is. So let me start off by introducing Hooke's law, which we already learned about when we first learned about springs, and I think it was in either the work. I think it was in the work chapter 7, or it might have been in the conservation of energy chapter 8. But either way, Hooke's law, in fact, says that the force applied by a spring on an object is equal to negative k times x, where x is the coordinate of the object, and what we'd consider the origin, the x equals 0 origin, would be what we call the equilibrium point on the spring. So at any particular point, if a spring is massive enough, or big enough, I should say, to hold a weight that you're going to hang on it specifically without springing so that it still obeys Hooke's law, then there will be an equilibrium position at which it hangs, or if you put it horizontally, there will be a horizontal position at which there's no compunction for the mass to be pushed away from the spring and no compunction for the mass to be pulled towards the spring. In both cases, that is what we would call x equals 0, and it's the equilibrium position. But by having this negative in here, that tells you something very important. So if you imagine the positive x direction being you stretching a spring and the negative x direction being you compressing a spring, then what you see is if the mass is moved to x being positive, then you have the force being in the negative direction, which is exactly what a spring does. It's a restorative force that when you stretch the spring in the positive direction, it pulls back in the negative. And similarly, if you have the mass on the negative portion of the x-axis, meaning you're compressing the spring, then the negative of x times k times the negative sign gives you a positive, and that's also what you expect to happen because as you compress the spring should push back in the forward direction. So just to give you an idea of why and how we look at that, I'm going to say this can be like our x-axis. This would be our y-axis. And what we'll imagine is over here somewhere is a wall and a floor. And what we have is a spring in equilibrium such that a mass, and this time I'm actually deciding to draw the mass and use the left edge of the mass as the indicator of position. It normally you would say make the center of the mass, but in principle you could use the left edge of the mass, or if it's hanging vertically, you could use the top edge of the mass. But you can also use the center of mass of the mass. You could also use the right edge of the mass, or if it's hanging vertically, the bottom edge of the mass. All of that's fine. But the main thing is, right now, we would consider this x equals 0 because I've chosen to use the left-hand side as the indicator of position. So if I were to, in fact, stretch it a little bit more, what you'd see is the spring would do something like this, and then the mass would be over here. And this would correspond to, let's say, x equals 1.4 centimeters, say. Now, x being 1.4 centimeters, if you multiply that by a constant k, which is going to be positive, and then times a negative 1, because that's makes up for the negative sign, then you'd see you get a force that is in the negative direction, which is exactly what you expect. Similarly, if you compress it by pushing the left edge of the mass to the left of the y-axis, then you have an x position that's negative, and multiplying negative k times that negative x gives you a positive, and that shows you the force is acting in the positive direction. So now that we've talked about that, we can also say, by the way, I mentioned this already, but I just want to give you again another idea about this. So here's a ceiling, and from it is a spring, something like this. And if we imagine that we have a box or a block or something hung on it, if this is where it hangs after you've let it relax, after you hung the mass on it and you just let it sit there for a little bit and it came to rest, then what we have to do is say that this is the coordinate origin, and this could be x in the positive direction, and this back here would be x in the negative direction, and this is x equals 0 for the equilibrium position again. So you can still do all that. Now, if we take Newton's second law, so Newton's second law says the summation of the forces is equal to mass times acceleration. Now, that only works if we're treating, well, it sort of only works if we're treating A as an acceleration as if it's a constant. But in general, A doesn't necessarily have to be a constant, in which case we can't put a letter there. We actually have to put a derivative, actually a second order derivative there, or a first order derivative if we're talking about in terms of velocity. In this case, we're just talking one dimensional motion, so this is going to become the summation forces in the x direction is equal to mass times acceleration in the x direction, which might in fact be the only acceleration we're dealing with. Since it's in the x direction and we know v is dx dt, then we know a is dv dt, which means d2x over dt squared. Okay, so that's how we allow for the acceleration to actually be a function of time. If we just left it in there as a symbol a, we'd expect that either to automatically come out with a t in it, or we'd have to solve a differential equation. Most cases, you don't get a force and a mass put in so that you can get a as a function of t, unless a happens to be a constant. So now if I go ahead and write the conservation of, or excuse me, Newton's second law for this mass on the spring, then what I'll have is this. Let's say this is a mass M. That's the mass that we have on the spring. And then our summation of our forces is just negative kx is equal to m d2x over dt squared. Now, if you take your statics course, that's probably where you're going to first learn about another way of writing the derivative. I was fortunate enough to have some of that in my calculus class, but I'm not sure everybody does. But when you take a derivative with respect to time, you can also write it with a dot. So another way of writing this would be negative kx is equal to mx double dot. So that means the second derivative of x with respect to time, whereas you might remember a derivative also can be marked by a little prime symbol. That's when you're taking the derivative of f with respect to x. So we use prime when we talk about a derivative with respect to x or with respect to y or with respect to z, but when we talk about derivative with respect to time, we use the dot. Okay, so it's just a much more clean way of writing it. But now what we can do is we can put all the equations or all the terms on one side and 0 on the other. When I do that, I get mx double dot plus kx is equal to 0. And this is the simple harmonic oscillator equation. So I want you to look at it. This is a fundamental thing that you're supposed to be learning from this chapter, and that you'll keep with you forever. Specifically, it is the equation for simple harmonic motion, SHM, as your book is calling it, and it's called the simple harmonic oscillator equation. That's why I called it SHO. Notice what it is. It's a constant times the second order derivative plus a constant times a zeroth order derivative. Okay, a zeroth order derivative just means the function itself, not with any derivatives being taken. So you have x of t. That's the zeroth order derivative. You have x dot. That's the first order derivative, and therefore is velocity. Then you have x double dot, which is the acceleration. So this is the simple harmonic oscillator equation, and any system that has a differential equation that's a constant times a second derivative plus a constant times a zeroth derivative equals zero is by default going to behave exactly like a simple harmonic oscillator. Okay, you'll see this in RC circuits. You'll see this in all sorts of stuff. RLC circuits, meaning AC circuits with resistors, inductors, and capacitors. You'll see it if you're trying to, for instance, study circular motion. One way you can represent circular motion is by assuming it's a oscillation in the horizontal direction and the oscillation in the vertical direction. All sorts of cool stuff like that. But the way we normally go about solving it, which isn't too important here, but you could divide both sides by m, and you get x double dot plus k over m times x is equal to zero. Now, when you look at a differential equation like this, you can sort of, you might not get it immediately, but after I tell you this, you should be able to make sense of it. There's certain functions that we've run into in calculus that when I take the derivative of it, it comes back as that same function with something times it. So, for instance, e to the x. If I take the derivative of e to the x, I just get e to the x. If I take the derivative of 4 or e to the 4x, then I get 4 e to the 4x. So you can see how the derivative is just like a scalar multiple of the original function. That kind of function should tell you, you should know that that kind of function would be an excellent solution here. And in fact, if you take differential equations, this is one of the early equations you'll learn is a simple harmonic oscillator equation. And what they do is they say, let's make a hypothesis. The hypothesis will be that x is equal to e to the rho t. So hypothesis x is equal to some constant, which we'll call a, times e to the rho t. And notice that's a function of t because we have dots there. If I had x double prime plus k over m x equals zero, then instead of t, I'd have a like a y there or something. Okay, and it wouldn't be x that we'd probably use. It'd probably be something like r that we'd use instead of x. But either way, the main thing is this is the hypothesis. Well, if you have enough experience with imaginary numbers, you know that, for instance, e to the I theta is equal to cosine theta plus I sine theta. And you also know that you could write, there's a way you can write sine theta in terms of exponentials. There's a way you can write cosine theta in terms of exponentials. So, for instance, sine theta, going on the assumption that I remembered Euler's formula, that's this e to the I theta equals cosine theta plus I sine theta. Going on the assumption that I remembered it correctly, that it's not sine plus I cosine theta, and I'm pretty confident it's not, then we can use that to get an idea of exactly what sine theta would be. And in fact, it should be since the, well, if I look at it this way, I can realize that e to the negative I theta would be equal to cosine theta minus I sine theta. And that's just from the fact that the sine of negative theta is negative of the sine of theta, whereas the cosine of negative theta is just the cosine of theta. So you can see that if you took e to the I theta, which gives you the positive I sine theta, and you subtract from that e to the negative I theta, what you'd see is because the cosine theta is the same in both the positive and negative one, then those two are cancel each other out, and all you're left with is, in fact, the positive 2 times the sine of theta times I. So all you have to do to make it sine theta is divide by 2I. Similarly, cosine theta is e to the I theta plus e to the negative I theta divided by just plain 2. So the main reason I'm bringing all this stuff up is, yes, this is stuff that will be very helpful to you in the future. If you learn this branch of mathematics, it can help you a lot. But the main thing I wanted to stress right here is that, yeah, in your differential equations class, they're going to use that hypothesis that x is equal to a e to the rho t. And somehow you'll ultimately get to being using sines and cosines, which is what Giancoli uses. So Giancoli is going to tell us that the solution to this equation is x is equal to a cosine omega t plus a phase angle phi. So that explanation with Euler's formula and the hypothesis and the ways of writing cosine theta and sine theta in terms of e to the I theta and all that good stuff, all of that was for me to let you understand why Giancoli is free to just say x equals a cosine omega t. But even more convincing is what happens when you go ahead and just substitute x equals a cosine omega t into the equation. So let's do that. I'm going to take, let's say, substitute x of t into the simple harmonic oscillator equation. So the true test of a differential equation, which by the way is an equation that relates derivatives of functions to one another and to other things, of course. So obviously mx double dot plus kx is a differential equation, and so is the other form that I wrote down here, x double dot equals, or x double dot plus k over m times x equals 0. That's another differential equation. And obviously, when you want to check whether something is a solution to a differential equation, all you have to do is plug in, take this solution that you think is a solution, take the derivative of it, and however many derivatives you need to fill in the equation, and put it all in there and just work out and see what has to be true, if anything, for it to be true. So what I'm going to do is start off with x is equal to a cosine omega t plus phi, and that omega is the omega that we're used to from circular motion. It's also called the angular frequency, and it's given by omega equals 2 pi f. So I'll write this over here just to remind you. Omega is equal to 2 pi f, and f is equal to 1 over the period. F is the frequency measured in hertz. T is the period, usually measured in seconds, but could be, years or whatever. And omega would be something measured in like radians per second. Now, in order for us to make any sense of whether this actually solves the equation, we've got to compute x dot as well. So x dot, remember, is dx dt, and the a is a constant, so that's going to just come out in front. But the derivative of cosine is, of course, negative sine. So I'm going to write a negative, and then I got to take the derivative of cosine, which would be negative sine. Then I got to take, using the chain rule, I got to take the derivative of omega t plus phi with respect to time, and the derivative of omega t plus phi with respect to time is omega. So I'm going to write that here, and now I'm going to write a sine omega t plus phi. So that's the first order derivative. That's called x dot. Now that we have that, we can compute x double dot, which is the second order derivative, like this. And in this case, we're taking the derivative of negative omega a sine omega t plus phi. Now, the omega, the a, and the negatives are all just constants. So I can put that out here. I can put the omega here. And in fact, the a is going to stay here too, but I'm leaving a little space because you're going to see something. I might need to write something on that omega there. Now, the negative omega a I just pulled out in front, and I need to take the derivative of sine omega t plus phi. So I can take the derivative of sine u and then take the derivative of u with respect to t, and that would be our chain rule. So the derivative of sine u with respect to u is just cosine u. Of course, u isn't very helpful, so I'm going to put in omega t plus phi because that's what u was. Now, the derivative of u, which is omega t plus phi, is just omega, so you can see that I left the space to put an exponent on the omega there. Okay, so that's our derivatives. Now I'm going to take and plug this into the equation, which is x double dot plus m over k, or excuse me, plus k over m, x equals 0. So when I plug that into the equation, the x double dot is negative omega squared a cosine omega t plus phi. Now I'm going to say the next term is plus k over m times just plain x, and x is a cosine omega t plus phi, and then all of that's supposed to equal 0. And while we're checking it, you can sort of write a question mark over it because you're not really completely sure whether it fits the equation yet. So it's a little unfair to say it equals it until we know. Uh, in this case, you can see the a cosine omega t is common to both terms. So we can write k over m minus omega squared times a cosine omega t plus phi is equal to 0. But remember, this differential equation is the equivalent of Newton's second law of motion, so it has to be true at all times. So the time dependence is just going to oscillate back and forth to give us what x is. So we can't rely on that. For all times to be equal to 0. That means the only way this equation fits the differential equation and makes it true is if the coefficient of the a cosine omega t is equal to 0, and that means that omega is equal to, we normally say plus or minus, but by convention we're just going to use the square root of k over m. So that's all that's necessary for this solution, x equals a cosine omega t plus phi. That's all that's necessary to make it satisfy the differential equation that we call the simple harmonic oscillator equation. So that's critical because now you see a second order derivative in time plus some constant, which in this case is k over m, times the zeroth order derivative is equal to 0, automatically has a solution x equals a cosine square root k over m parentheses t plus phi. Okay. In other words, the omega is the square root of k over m. Okay. And that's set up. Now we still have two unknowns. We still have the a and we still have the phi, and that's an intentional thing on a second order differential equation. Just like a second order polynomial has two solutions, a second order differential equation has to have two free variables as well, so that it can be established what those are from the initial conditions. You can sort of think of it as you're trying to undo a derivative. And what function do we use to undo a derivative? Anyone? Or what mathematical operation do we use to undo a derivative?
An integral.
Exactly. In fact, when you learned it in calculus, they called it the antiderivative. That was why, to get you to feel for that. So you know that in order to get rid of x double dot, you're going to have to take an integral of it. But when you take an integral without a limit of integration, what do you have to add to the integral? Do y'all recall anything about that? So if I integrate, for instance, 2x, I get uh, x cubed. Wait a second. No. Uh, you have to add one and then divide by the one. So it's 1/3 or 2/3 x cubed, right? But that's not quite right. When I say the integral of 2x squared, exactly, that's what I was going for, Gabe. When I say the integral of 2x squared, or excuse me, of 2x, and I say the answer is 2/3 x cubed, that's not exactly right. But in fact, you could say the answer is 2/3 x cubed plus 1, or 2/3 x cubed plus 0.0892, or 2/3 x cubed plus 0.0971. It doesn't really matter. The main thing is, yes, you have to add an integration constant. So that's how we arbitrarily sort of can think about solving a differential equation. If it's a double or a second order differential equation, meaning the highest order derivative is 2, then we're going to have to integrate it twice. Each time you integrate, you have to add an integration constant. So you could tell, since this is a second order derivative, you should expect to have two integration constants. And that's why I had to have both the a and the phi in the cosine function, or in the x equals a cosine omega t plus phi function, to account for the two initial conditions that are necessary to figure out what the two c's are. So that's a nice way of thinking about it. Just keep that in mind. Now that we have this as background, I'm going to show you how we can apply this in various settings. Now remember, this is the differential equation. And remember, this is the solution, x equals a cosine omega t plus phi. So no matter what the system is, if you see something oscillating, meaning you graph its position as a function of time, or you graph its amperage as a function of time, or you graph its voltage as a function of time, or you graph its brightness as a function of time, and it looks like a cosine curve, then you know in some sense there's a differential equation that looks just like the simple harmonic oscillator, that relates to those variables, whether they be voltage or amperage or brightness or whatever. Okay, so it goes both ways. You can say, hey, if I have this differential equation that is a constant times x double dot plus a constant times x equals 0, then the solution is automatically going to be x equals a cosine omega t plus phi. But the other way is, if I see that some variable is given by x or y or z or d or or q or whatever is equal to a cosine omega t plus phi, then you know there exists a differential equation such that you can write it x double dot plus some constant times x equals 0. So now we're going to make use of that stuff by solving various examples. I'm going to start off with the example in your textbook, which is example 14.1, and it says car springs. So this is example 14-1, and this is, again, like I've been advising you, make sure you have your book out, but I'm also going to read it to you, so hopefully that will help. Example 14.1, car springs. When a family of four with a total mass of 200 kilograms step into their 1,200 kilogram car, the car's springs compress 3 centimeters. What is the spring constant of the car's springs, assuming they act as a single spring? And B, how far will the car lower if loaded with 300 kilograms rather than 200 kilograms? This is a very typical Hooke's Law type problem, and we probably had something similar to it when we first encountered Hooke's Law in chapter, I think it was 7. So let's go ahead and write down what we know. We know the mass of the people. I'm going to call that lowercase m is 200, and I'm going to treat that as if it's 3 sig figs, so it's 200 kilograms. And we know the mass of the car is 1,200 kilograms. And actually, before I write that unit, I'm going to go ahead and put a 0 and lock that down as if it's 4 sig figs. And that's not consistent with what the book did, by the way. I just want to remind you of that. That caused a stretch x that's equal to 3.0 centimeters. Okay, and in part A, what they want to know is what is the spring constant. And then in part B, what they want to know is how far will the spring lower the car if 300 kilograms is there. So what is X if M equals 300.0 kilograms. So that's what part B is. So let's work on solution. What we're using here is F is equal to negative kx, which is Hooke's law. And remember that negative is about telling us that this is what we call a restorative force, meaning if you stretch it in the x position, the force is going to try to pull it back to where it was. So if you stretch it in the positive x direction, it's going to pull back in the negative x direction in hopes of getting it back where it was. And if you compress the spring by pushing it in the negative x direction, the force is going to act in the positive x direction to try to put it back where it was. That's a restorative force. You need that in order for it to be a restorative type force, and there's an example on that later. So now that we have that, we know that when we're talking about magnitudes, we can also just drop it and just say F is equal to K times X. Now in this case, the force F is got to equal M plus M times G. And with that, we're just using the fact that weight equals mass times gravitational acceleration. So the force in this case is going to be 200.0 kilograms plus 1200.0 kilograms times 9.80 meters per second every second. And that should give us our weight in newtons. And when I do this math, that's going to be 1400 times 9.8. That's 13,720 newtons. Now, in this case, we actually had 1200 plus 200. That gave us actually 4 sig figs. So we do have 4 sig figs, but that means the ones place is not represented. Oh, okay, the addition gave us 4 sig figs, but multiplying by 9.8 reduced it to 3 sig figs, so I got to underline the 2. So this number is only good to the nearest hundreds. We'd have to call it something like 1.37 times 10 to the fourth if we were sticking with our significant figures data, okay, our paradigm. So with that in mind, now I'm going to say F equals K times X. So I'm going to say 13,720 newtons is equal to K times, I want to keep this in the standard SI unit, so I'm going to convert the centimeters to meters, and that'd be 0.030 meters, and therefore K, the spring constant, that's what that's called, the spring constant is 1,300, or excuse me, 13,720 newtons divided by 0.030 meters, and that gives me 4.57. Now notice by dividing by 0.030, I've reduced the sig figs to just 2. So when I write 4.57, I'm already using one extra digit than the sig figs allow. I'll go ahead and write 2 just for safekeeping. And I'm going to say that's 4.573 times 10 to the fifth. And that's in units of newtons per meter, which is what the units of K normally are. Anybody have any questions on that part? Okay, so now what they want to do is they now want to say, well, what is actually going to become of X if I replace the 200 kilograms of people with 300 kilograms of people? Well, we know that the force is going from 1400 to 1500, right? So we could, in principle, just say 15 over 14 times the 3 centimeters, and that should give us the right result. Oops, my computer just decided to kick me out of Pearson. Across the board, it decided to kick me out of Pearson. That's not helpful at all. Let's try it again. Anyway, so let's. That's one way we could do it. We could just say 14 because the x is directly proportional to force, and the way we get this new force for 15 1,500 kilograms instead of 1,400 kilograms is we could just say 1,400 over 1,500 over 1,400 times the original 1,400 would just give us 1,500. We could do that same thing with the x, and when I do that, I'd say 15 divided by 14 times 3. The 15 divided by 14 is 1.07. It's 1.07142857, so on and so forth. But in this case, it's going to give us 3.57. So that's just one way we can do it by just thinking of the concept that, hey, if I double the force, I double the x. If I triple the force, I triple the x, because F is proportional to x. So that's always a good way to do it, just to get a rough approximation. But in this case, now we're going to say F is equal to 1,500 kilograms times 9.80 meters per second is equal to K, which we know is 4.573 times 10 to the fifth newtons per meter times X. That gives us X is equal to 1,500 divided by our times 9.8 gives me 14,700 newtons, and that technically only had 3 sig figs, so I got to underline these two zeros. Now I'm going to divide that by 4.573, and the 7 and 3 are not sig figs, times 10 to the fifth newtons per meter. And you can see that a newton divided by a newton per meter is just going to give us meters. So I'm going to take the 14,700, and I'm going to divide that by 4.573 times 10 to the fifth. And that gives me 0.03215 meters. Now I've got 3 sig figs on the top, 2 sig figs on the bottom. That means the 1 and the 5 are not sig figs. So this is approximately 3.2 centimeters. And that's the answer to part B. Now, I suggested that the x could have also been 1,500 over 1,400 times 3 centimeters. And when I did that math, I got a slightly different number, but that might have just been because I was using more sig figs than supposed to. So let's look at it now with just keeping in mind that we only have 2 sig figs. 1,500 divided by 1,400 gives me 1.07 times 3 gives me, yep, 0. 1,500. Whoa. Oh, I divided by 3. There's the problem. So 1,500 divided by 1,400. I can't believe I did that, but anyways, I seem to have divided by 3 instead of multiplied. That's why I got the weird number. That makes a lot more sense. Now I'm going to say times 3, and this gives me 3.2143, which we have no reason to suspect that it should be better than 2 sig figs. So we at least see that to 2 sig figs, it's 3.2 centimeters, which is exactly the same answer we got the other way. So that's a good check. Anybody have any questions on that? Now I'm hoping that this is going to allow me to open the textbook again since it just kicked me out at random for some reason. And not only that, let's hope it opens to the same page I was on, which it normally does do that, so that shouldn't be a problem. Does anybody have any questions about this so far? Okay. So one of the other things we learned about the simple harmonic oscillator is that the solution is x equals a cosine omega t plus phi, and that is by necessity because the shape of cosine is like this. That means the position is going to go like that as well. And with a position that oscillates back and forth between some maximum, some minimum, and then back to the maximum again, right? With that kind of motion, there's something called a period and a frequency. So we've learned that that angular frequency omega is the square root of k over m. So that should at least help us to understand that we can solve other types of problems too, not just ones about how far a spring will compress, but what if, for instance, like in the movie Uncle Buck, that car hits a speed bump or a dip in the road or something like that, it's then going to go into oscillatory motion. And we would say, well, what is the period or the frequency of that oscillatory motion? And we'd know how to do it because all we had to have is either the omega or the k and the m. So now that we've done example 17.1, or excuse me, example 14.1, let's go for example 14.2, which is in the next section. Example 14.2 is a conceptual example. I really like it. It says, and this is one I'm not going to write down, but I'll read it to you. Conceptual example 14.2 is the motion simple harmonic. So they're asking a question: is the motion simple harmonic? Which of the following forces would cause an object to move in simple harmonic motion? So remember, I told you the simple harmonic motion is a result of the restorative force. If a force isn't restorative, then it can't create simple harmonic motion. So actually, I am going to write it down. Whoa, another conceptual example. 14-2, and we've got F is equal to negative 0.5 x squared. We got F is equal to negative 2.3 times y. We've got F is equal to 8.6 times x, and we've got F is equal to negative 4 times theta. So we got to see whether this force is restorative or not. So if I were to take the first case, which is this one, if I plug in x equals a positive number, then the force pulls in the negative direction. That seems like it's restorative. But what if I plug in x as a negative number? Then by taking the square of it, because clearly the exponent is 2, then the square of a negative number is positive and it still pulls in the negative direction. So what that means is if I push something in the negative direction, it's going to take off and get even more force to the negative direction. So that can't restore. So we can immediately say that that one's not going to work. What about F equals negative 2.3 times y? Well, the fact that it's y instead of x doesn't really matter. All we have to know is that if I have a y that's positive, it should make a force that points in the negative direction, and if I have a y that's negative, it should make a force that points in the positive direction, and that's exactly what this one does. So this is a restorative force, and therefore it should be able to cause simple harmonic motion. If we look at the next one, F is equal to 8.6 times x, that has the x like we like it. It's not x squared. So when I plug in an x being positive, I get a positive force. But when I plug in a negative, I get a negative force. So in this case, it's actually sort of like the case of F equals negative 0.5 x squared, except in both ways it goes wrong. So for instance, the F equals negative 0.5 x squared was good as long as the x was a positive number, but when the x was a negative, then you'd push it to the negative direction and that would cause the force to get bigger. And as the x got bigger in the negative direction, the force would get bigger still. And as that got bigger, it would get bigger still. So it really is like a runaway train or something like that. It's almost like a perpetual motion machine. So that was a problem. In this case, we have it failing both directions. So when I have F equals 8.6x, if I put in a positive, the force is in the positive direction. That means it's not trying to restore it. And if I put x as a negative, it's not going to push in the positive direction. It's going to get a positive force, or it's going to get a negative force as well. So it's actually sort of it's sort of like a perpetual motion machine in both directions. If I push it to the right, it's going to not only move to the right, but then the force is going to get even bigger to the right. And then as that moves further, the force is going to get bigger. And as that moves further, the force is going to get bigger. And the same thing happens when you push it in the negative direction. So this one's going to be a no as well. Now the F equals negative 4 times theta, that looks just like F equals negative kx. Remember, one of the key things you should be learning from all these years of algebra and now physics is that the symbol that you use is irrelevant. So this looks like F equals negative k times x because it doesn't matter whether you call it a k or 4. It doesn't matter whether you call it a x or a theta or a y, and it doesn't matter if you call it a f or some other variable. In this case, they did choose f though. So in this case, this one's going to work as well. So it appears that only B and D are forces that are capable of making simple harmonic motion. Any questions on that? All right. So I've already mentioned to you how the omega is related to frequency and how that's related to period and all that good stuff. So let's move on to example 14.3, and I think I can fit this uh, in the remainder of this page. So there it is. This is example. Darn it, I hate that thing. Example 14-3. And it says car springs again. Determine the period and frequency of the car from example 14.1 after hitting a bump. Assume the shock absorbers are poor so the car really oscillates up and down. So what we want to know is from example 14.1, what is, they said the period and frequency. What is T and F? So what we know from plugging in our x equals a cosine omega t plus phi, what we know from that is that the omega has a very specific form. And x double dot plus k over m times x equals 0. These combine to tell us that omega is equal to the square root of k over m, but we also know that omega is 2 pi times the frequency, and that frequency is 1 over the period. So that's what we need to know. Now, in this case, we're talking about the frequency, and we're going to assume it's the original load of people, not the 300 kilograms, but the 200 kilograms of people. So with that in mind, we can say omega, which is equal to 2 pi f, is actually going to be the square root of k over m. We already found that k was 4.573. Now you see why I kept the extra digits, more than just one extra digit. Two would be better. So 4.573 times 10 to the fifth newtons per meter. And then that's divided by m, which in this case is 1,400 kilograms. Remember, it's the total mass that's in the vehicle, and we're assuming it's the mass with the original load of people, the 200 kilograms, not the 300 kilograms. So I can take 14 or 4.573 times 10 to the fifth and divide it by 1400, and that gives me the square root of 326.64. Now I'm going to take the square root of that, and that gives me 18.073, and this is technically radians per second is what that comes out to be. If you work it out, a newton is a kilogram meter per second squared, so a newton per meter is a kilogram per second squared. And then if you divide that by kilogram, you just get a per second squared. And then you take the square root of a per second squared and you get a per second. And as I told you, a radian is just a pure number. So I can throw a radian in there because that's what we know the unit should be in omega. So that's our omega, but that also tells us that F, which is what we wanted to know, not omega, we want to know the frequency in the period. The F is 18.073 divided by 2 pi. Now, the 0 and the 7 and the 3 are not sig figs, but still, I'm going to go ahead and take that and divide the 18.073 by parentheses 2 times 3.14159 close parentheses, and that gives me 2.876. And this comes out in cycles per second, or what we call hertz. Now, I'm only supposed to have two sig figs, so I'm underlining the 7 and the 6, but everything else should be fine. So that's our frequency. We'd say it's roughly 2.9 hertz. And now, if we want the, whoa, Nelly, what's going on here? Oh, I got a different K value than they did. Anybody see any mistakes on my K value? Did I do a division over there when I was supposed to do a multiplication or anything? The physics I've done here is correct, but I'm looking at, I just pulled up their solution, their answer for problem 14.2, and they're not using K is 4.573 times 10 to the fifth. They're using K is 6.5 times 10 to the fourth. So I clearly, well, I'm assuming I clearly made some kind of mistake somewhere in terms of arithmetic, but I'm not seeing it. Let's, did anybody find any error yet? Doesn't look like anybody did. Well, we'll address that. Let me go ahead and work as if this is right, and we'll deal with it. Now, the period t is equal to 1 over the frequency, just like the frequency is equal to 1 over the period. So what we can do now is t is equal to 1 over f, which in this case should be 1 divided by the answer I just calculated. And that gives me 0.3477 seconds. Again, that's only good to 2 sig figs, so I have to do that. So all of this is questionable because the K is questionable. K is questionable. And now, when I say questionable, I just mean the physics we did was perfect. There's no problem with that. But in some sense, I got a different answer than the book did. So just to look real quick, I'm going to say 200 plus 1200 is 1400. So 1400 times 9.8. That was 13,720. That's the same thing I got. Now that's supposed to be the force, and that's supposed to be equal to K times X, and the X was zero point zero 0.03 meters. So if I take the F and divide it by zero point zero 0.03, that gives me 4.573 times 10 to the, oh, stupid head. I stand corrected. If we read the problem, actually, and it's worse. It's worse than I told you guys. I apologize completely. I'm going to turn back to the previous section of to example 14.1 and show you the part of the reading that I wasn't paying attention to. It says when a family of four with a total mass of 200 kilograms steps into their 1,200 kilogram car, the car's spring compresses. So what happened was I was taking it as if we were just putting all the mass of the people in the spring and the car on the springs and seeing how much it depressed. But in reality, what it said is when a family of four with a total mass of 200 kilograms strips into the car, that was supposed to be how we got K. So there's the problem. I'm just going to fix that by writing this up here and say, I'm going to write in red to correct it for you guys. I prepped for this like 3 days ago, so I completely waited too long, evidently, because I completely forgot. And obviously, the meaning was pretty obvious that it was supposed to be the people. This should have just been M times G, and M times G would be 200 times 9.8, which would be 1,960 newtons. Let's double check on that because there's clearly I can make some mistakes. 1,960 newtons. So I'll say 1,960 newtons and 1,960 newtons, and now 1,960 newtons, and now divide that by 0.03, and that gives me 6.5 times 10 to the third. And it actually gives me 6.533 times 10 to the, and I said third, it's actually 10 to the fourth newtons per meter. That's what K is. So that's actually the correct one. Now that means all of this would be a problem too, because I'm not supposed to take 14,700. I'm just supposed to take 300 kilograms times 9.80 meters per second, and 300 times 9.8 is equal to 2940. 2940 divided by 6.533 times 10 to the fourth gives me 4.50 centimeter, or gives me 0.04500 meters, which is 4.50 centimeters, and that's one extra sig fig there as well. This one should have had three sig figs at most. So that fixes all that. And now if you take x is equal to 300 over 200 times 3 centimeters, you would get exactly 4.50 centimeters. So that's what I was shooting for. This again is 6.533 times 10 to the fourth, and that gives me a slightly different angular frequency, 6.533 times 10 to the fourth divided by 1400. So that time we are supposed to use 1400 because that's the oscillation of the whole thing. That gives me 46.66, which I'm raising to the zero point 0.5 power, and that gives me 6.83. 6.831 radians per second. And of course, dividing this by 2 pi gives me 1.08, 1.087 hertz. And of course, the 8 and the 7 are not sig figs, so that's the right question. Now, if I do that, this frequency, or excuse me, this period's not right either. It's 1 over 1.08. So I'm going to raise that to the negative 1 power, and that's going to give me 0.9198 is equal to the period. All right, so sorry about that, and turned out it was more than arithmetic error. It was a complete misreading of the. Well, it was a misreading, but it's also bad physics because I misread it, but the result was me doing the physics wrong, so that's not good. So everybody follow what was right versus what was wrong. Ah, Gabe did catch me on that and was giving me a what I'd done wrong. So thank y'all for that. I'm sorry I screwed that up. That was really bad. This is supposed to be pretty trivial stuff, and I just made a simple problem into a nasty problem. Sorry about that, everyone. Now that we have that, let me go on to the other stuff. And by the way, these are the types of examples that you should be ready to do both on the last online test as well as in the final exam, which is face to face. So I'm having a very small fraction of chapter 14 and 15 type problems on that test. So just keep that in mind. These examples are sort of the archetype of what you're supposed to be expected to do. Hopefully you won't, have a brain fart like I just did with two problems in a row, but other than that, we're good to go. Any questions, anyone, before I move along? Ah, so here's another one, and this is what I was talking to you about when I said, hey, if you have anything that exhibits motion like this, meaning the variable on the y-axis could be voltage or acceleration or position or current or the intensity of sound or the brightness of light. Doesn't really matter. Any variable on the vertical axis that traces out a sine or a cosine curve, you can think of it as coming from a differential equation that fits that sine or cosine function. And similarly, if you see a differential equation that is like a number times x double dot or a double dot or d double dot or c double dot plus a number times x or c or d, whatever the variable was, equals zero, then you know it has a solution given by x equals a cosine omega t plus phi. So in this case, we're going to do a spider web, which is example 14.4. So example 14-4, and it says estimate. It says a spider of mass 0.30 grams. So I'm going to write M equals 0.30 grams. A spider of mass 0.30 grams waits in the web of negligible mass. A slight movement causes the web to vibrate with a frequency of 15 hertz. A, estimate the value of the spring stiffness, and B, at what frequency would you expect the web to vibrate if an insect of mass 0.10 grams is added? So that's our question. Read it again. A spider of mass 0.30 grams waits in the web of negligible mass. A slight movement causes the web to vibrate with a frequency of about 15 hertz. Estimate the value of the spring stiffness K for the web, and B, at what frequency would you expect the web to vibrate if a insect of mass 0.10 gram is trapped in addition to the spider? Okay, so this is a case where we have no reason necessarily to believe that the simple harmonic oscillator equation applies to it because we haven't learned any physics about a spider web. But if you've ever watched a spider web and see something moving on it or fly, you've definitely seen the spider web do like this or like this. And that looks like oscillatory motion. And oscillatory motion is sinusoidal motion, and sinusoidal motion is cosinusoidal motion, so that we know that x equals a cosine omega t plus phi is a solution for some position x on that spring, I mean, on that web. So let's go ahead and write this out. We have the solution, and what we're going to make use of is omega, the angular frequency, which is 2 pi times the regular frequency, is equal to the square root of k over m, like that. And what that means is f is equal to 1 over 2 pi times the square root of k over m. Now, what we know is k and or excuse me, what we want to know is K, but what we know is F and M. So we can go ahead and put all this in there and then solve accordingly. I will go ahead and square both sides, and that gives me F squared is equal to 1 over 4 pi squared times K over M. So for part A, I'm going to say K is equal to 4 pi squared F squared over, or excuse me, I think that might be times m. Yeah, that's times m. So it's 4 pi squared F squared times m. That means 4 times 3.14159 squared times 15 hertz squared times 0.00030 kilograms. So when I do all this, I'm going to say 4 times 3.14159, that has to be squared, times 15, which has to be squared, times 0.0003. This should give us only 3 sig figs, but I get K is equal to 2.6648, and that should come out in newtons per meter. But that's a lot harder to see in this case. You'd have to break down the hertz, and the hertz is in units of newtons per meter per kilogram square root. So ultimately, we just have to sort of trust it. But we only have 2 sig figs, so I'm going to underline the last 3 digits, and we're going to say this is in newtons per meter. Anybody have any questions on that one? Call it about 2.7. Now for part B, they want to know what would the frequency be if the mass is now not the mass of just the spider, but the mass of a spider plus another bug on it. Okay, so with that in case, I say another bug. I know that's not necessarily biologically correct, but the main thing is we're going to say F is equal to 1 over 2 pi times the square root of K over M. So this is going to be 1 over 2 pi times the square root of 2.6648 newtons per meter divided by, now the mass was 0.00030, but now we're adding a zero point 0.10 grams to it, so it's 0.00040 kilograms. That's what the mass is now. So I'm going to take this 2.66478 and I'm going to divide it by 0.0004. That gives me 6,661.97. Now I'm going to take the square root of that. Now that gives me 81.6209. Now I'm going to divide that by 2 pi. And when I do that, I get 12.99. 0 hertz. So it was 15 hertz, but now it went to approximately 13 hertz. Any questions there? Now, this one's kind of neat just because it applies and it makes some sense. And you can also sense from that that, that's one of the things that the spider could use to indicate to it that, hey, something's on my web. I can feel it shaking, and that shaking could be an earthquake, could be wind, could be all this. But if it stays even after the wind stops, the spider might actually be smart enough to figure out, hey, there's something on this web with me. Let me go investigate. And the web being sticky like it is has some probability of sticking the bug to it in such a way that it can be held hostage until the spider comes along and kindly sets it free. See how that ended in a happy story? Anybody have any questions? All right. Now, this is something that's kind of neat, and in order for us to do this next example, which is example 14.5, I need you to understand something about what's going on with this new function. So let me go ahead and separate this and give you some of the background material. So what we found was x of t is equal to a cosine omega t plus phi. And we know that v of t is equal to dx dt, which we know we call x dot. Because of that, we see v of t is equal to negative omega a sine omega t plus phi. And in addition to that, we know a of t is equal to dv over dt, which we could write as v dot, but we could also write that as x double dot, in which case a of t becomes, in this case, the derivative of sine is cosine, so we're still going to have this negative, and it's going to be negative omega squared a cosine omega t plus phi. Now, the reason why I want you to see that is I wanted you to realize when we actually graph this, if we graph this as x as a function of time, and this is t. I don't know why I labeled that x down there, but anyways, I did. Okay, so x as a function of time means if I assume phi is equal to 0, then I would get basically something like this. It would go from here to here, and then down to here and two more, and then back up to here and two more, and then back up to here and two more. So we're making a sinusoidal graph. Well, a sinusoidal graph, which comes down like this, and so on. And you just see that repeats. So what this is right here is x max. And of course, x minimum would be the same as x max, only it's negative. So, and in fact, we know that x max has to be equal to a. So we see that a really is the amplitude of the oscillation. Now, if we treat v of t, what we're going to see is v of t is actually a sine function, and it's actually a negative sign. So I could write it like this, and they both have the same frequency, by the way. So I'm going to take and say it starts here. This is going to be v of t, and then it's going to reach right about here, and then it's going to reach right about here, and then I'm going to go over again by two more units, and it's going to reach a max here, and then I'm going to go over by two more units. It's going to reach a min here, and then here, and then here. So this right here, I'm using sort of an arbitrary scale for the vertical axis, but the main thing is you get the curves, how they line up vertically with each other. That's v of t. And we see that this is, well, I shouldn't write it that way. We see that this is, that quantity is v max. And v max is clearly omega times a. Now, if we soup it up even further, and let's try another variable, this time we're going to plot a of t. A of t is a negative cosine function, so what I'm going to do is I'm going to say negative, it starts here, then it's going to be here, then it's going to be here, then it's going to be here, then here, then here, then here. So this is our acceleration as a function of time. And in fact, we can see that this height right here is A max, and clearly A max is omega squared A. So that's what we needed to understand about this motion. We needed to understand that the amplitude of the oscillation is related to the velocity and is related to the acceleration, and the thing that couples them together that makes them related is the amplitude is A, the max velocity is omega A, and the max acceleration is omega squared A. So now we can start to move into other variables where we can understand, hey, if I see something oscillating and I can work out its frequency and its amplitude, I can immediately tell what its max speed is going to be, and I can immediately tell what its max acceleration is going to be. And if you study physics long enough, or if you go, for instance, into structural engineering or something like that, you'll know that basically the acceleration that a body has, let's say, imagine a house being accelerated by an earthquake, or a house part of a house being accelerated by a high speed wind, you know that what you have to design the house for is what that acceleration is so that it can withstand it without falling over or something like that. So this is a way, without knowing all the details, of figuring out exactly how strong to make, for instance, a floor or something. And that's what brings us to example 14.5. So let's look at example 14.5. And it says estimate a vibrating floor. A large motor in a factory causes a floor to vibrate at a frequency of 10 hertz. The amplitude of the floor's motion near the motor is about 3 millimeters. Estimate the maximum acceleration of the floor near the motor. So A max is what we want to know. So all we're given is the frequency of oscillation of this floor. And you've probably been somewhere where the floor bounced up and down a little bit. Maybe, hopefully, it wasn't just in everyday life. But for instance, if you just go into Greenbrier Mall, and parts of Lynn Haven Mall might do the same thing. I just know that when Greenbrier Mall was first built, I was actually, I'm old enough to remember when that happened. Various architects and engineers were complaining that they had done something not necessarily that great in designing it, in that the floors would actually shake as people walk. And if you ever walk through Greenbrier Mall, especially if you're upstairs, you could feel every now and then the floor would just start to shake like that. Obviously, it lasted long enough because it's essentially going out of business now. They're going to get rid of that mall, but no one was hurt or anything, so that's good. But in this case, we have a floor that's oscillating, and we can use that to calculate, more or less what the acceleration is, and that would tell us, hey, uh, maybe we should, take those 2x8s that's holding that floor up and replace them with 2x10s, or maybe we should replace it with 2x12s or something like that. And that would all be, of course, something you could calculate if you had a knowledge of structural engineering. So with that in mind, this is just asking for the maximum acceleration, and what we know is A max from the stuff I just showed you was omega squared A, and omega is 2 pi f. So solution A max is equal to omega squared A, and omega is equal to 2 pi times f. So we're going to say 2 times pi times 10 hertz. That quantity is going to be squared, and then I'm going to multiply it by 3.0 times 10 to the negative third meters. And that's just so the units work out. Notice when we take 2 pi, that's a conversion of 2 pi radians per hertz, or 2 pi radians per cycle. So hertz being cycles per second, that converts it to radians per second. So now I can take the 2 times 3.14159 times 10, and that gives me 62.8318. I'm going to square that. That gives me 3947, and now I'm going to multiply that by 3 times 10 to the negative third, and that gives me 11.844 meters per second. So this is greater than the acceleration due to gravity, and because of that, that means if you have an object sitting fairly close to the machine on this floor, like a chair, at some point that floor is going to accelerate down so quickly that a chair is going to be left aloft and then fall down and hit. So you're going to hear blank, 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 something like that. And not only that, it's going to structurally damage the material over time. So that's it. Anybody have any questions on that one? So you can see now how just having this knowledge of oscillatory motion allows us to make certain calculations and stuff of that sort. Now, the other thing to understand about differential equations in general is in order to solve them, like I said, you're sort of imagining the solution of a second order differential equation as being found by integrating twice. And each time you integrate, you're introducing integration constant. So integrating twice means you have two integration constants, which means you have to have two equations to uh, to actually satisfy and figure out what those constants are. Normally, what we do in solving a differential equation that's second order is we have x, the variable that we're actually solving for. Remember, it's x double dot, and we're trying to solve for x of t. So the x, what we normally have is that at t equals 0, or what we would like to have is that at t equals 0. And then you could have the velocity v of t at t equals 0. That's a normal two sets of equations that would give us, and I say it's an equation, it's really just a data point. It tells us, hey, at t equals 0, the velocity was 4.7 or negative 3.2 meters per second. And hey, at x equals 0, the position was 0.14 meters. That is a statement that allows us to plug that into x equals a cosine omega t plus phi for the x, or or v equals negative omega a sine omega t plus phi. You can plug that in, and in both cases, that allows us to figure out what a is and or what phi is in the as the phase constant. So this is an example that will show you a little bit about that, and then the next example shows you even more. So here comes example 14.6. If anybody has any questions, feel free to ask. So this one says, starting with x equals a cosine omega t. The displacement of an object is described by the following equation where x is in meters and t is in seconds. Determine the oscillating object's a, amplitude, b, frequency, c, period, d, maximum speed, and and e, maximum acceleration. So what we're given is x of t is equal to 0.30 meters times cosine of 8.0 t, and technically that's coming out in radians. So I put those units in parentheses just to make sure you understood what was going on there. Your book just wrote rad right beside it, and it looked a little confusing. But what we want to know is A, we want to know the amplitude, which we called A. In part B, we want to know the frequency, which we call F. In part C, we want to know the period, which we call T. A lot of this stuff is just about knowing what variables correspond to what quantities. For D, we want to know the maximum speed, Vmax equals question mark. And for part E, we want to know the maximum acceleration, uh, yeah, Amax. So that's what we got to do. Now, the big thing is to remember that the general form solution, the general form is x of t is equal to a cosine omega t plus phi. Now, looking at that, and I also should say v is equal to negative omega a sine omega t plus phi, and a is equal to negative omega squared a cosine omega t plus phi. So now if you look at the purple version of x of t and the x of t in blue, can anybody tell me what a is? This is supposed to be real easy. If you're thinking it's too easy and you don't want to answer it, you're probably thinking correctly, that it's the right answer. So remember the amplitude is the coefficient, exactly, Gabe. The amplitude is the coefficient of the sine function for x equals, or excuse me, the coefficient of the cosine function. And in actuality, remember the amplitude of any cosine or sine function is whatever the number that is out in front of the sine or cosine function. So yes, in this case, A is equal to 0.30 meters. Now for part B, they want to know F. Well, remember omega is the coefficient of t in the argument of the cosine function if you have the function x of t. If you have the function v of t, it's the coefficient of t in the sine function. If you have the a of t, it's again the coefficient of t in the cosine function. So just looking at this, we can see that omega is equal to 8.0. And the fact that it says radians over there tells you that, oh, that 8.0 must be in radians per second because the t will be in seconds. And when you multiply radians per second times seconds, you get radians. So this omega is in radians per second, and that's equal to 2 pi times f. Therefore, f must be equal to 8.0 radians per second divided by 2 pi. So F is going to be 8 divided by 2 times 3.14159, close parentheses. And we get F is equal to 1.273 hertz. And we really only had two sig figs, so I got to underline the 7 and the 3. But that is our frequency. Oops, I'm supposed to be doing that in purple. Any questions on that one? All right, now C, they want to know the period, and that requires us, I didn't write this in our solution line, so I should write it F is equal to 1 over the period, but I could also write this as T is equal to 1 over the frequency. So either of those would work. I'm going to use T equals 1 over the frequency, which is 1 over 1.273 hertz. So I'll raise this to the -1 power. I still have the frequency listed in my calculator. So this is going to be 0.7854. Whoa. And that is seconds. And of course, it's only good to 2 sig figs. So I have to underline the 5 and the 4. But this should be equal to the period. Any questions on that? All right, now we can move on to part D, which is Vmax. And remember, Vmax is omega A. So we're going to take the 8.0 radians per second and multiply that by the A, which is 0.30 meters. And of course, 8 times zero point 0.3 is 2.4. So this is going to be 2.4 meters per second. Remember, we can toss the radian anytime we want because it's technically a pure number. So 2.4 meters per second should be the Vmax. Similarly, we can do part E. And part E, they want to know A max. And we know A max is omega squared A. So this is going to be 8.0 radians per second quantity squared times 0.30 meters. Now, 8 squared is 64. 64 times 3 would be 180, 192. So dividing that by 10 would be 19.2. So the acceleration should be 19.2 meters per second. Every second is A max. Any questions on that? Oops, don't know what I did. red, should have been purple. Okay, so a lot of this thing that you're learning in physics is recognizing that certain equations have certain forms, like the equation x of t equals a cosine omega t plus phi, and then you look at something like x equals zero point 0.3 cosine 8t. That should tell you, oh, well, A is 0.30 meters, and hey, omega must be 8.0 radians per second, and hey, phi must be zero in that case. That's a lot of what physics is once you figure out the equations, you should be able to look at representations of those equations and immediately be able to decipher the variables that are in it. So, just keep that in mind. That's largely what this chapter is about, is you being able to apply that. So let's look at another example. This time it's example 14-8. Anybody have any questions? Oop, it's 14-7, not 14-8. So 14.7 says loudspeaker. The cone of a loudspeaker oscillates in simple harmonic motion, what they call SHM, at a frequency of 262 hertz, which is middle C. The amplitude of the central part of the cone is A equals 1.4 times 10, or excuse me, 1.5 times 10 to the negative fourth meters, and at T equals 0, X equals A. This is where we're starting to get into initial conditions for a differential equation. A, what equation describes the motion of the center of the cone? B, what are the velocity and acceleration as functions of time? And C, what is the position of the cone at t equal 1.00 milliseconds? So I got to write down the information they gave us. They said F, the frequency is 262 hertz, which helps you to know that that's middle C. A, the amplitude of oscillation for the central part of the cone, the dead center of it, in other words, is 1.5 times 10 to the negative fourth meters, and at t equals 0, x is equal to a. For part A, they're wanting to know what equation describes the motion of the center of the cone. So that's x of t is equal to question mark. For part B, they want to know what are the velocity and acceleration as functions of time. So v of t equals question mark, a of t equals question mark. And again, you're seeing this is one of those cases where we have some kind of form representing, in this case, x of t, and we're going to put in the form the various parts, the a, the omega, the phi, that sort of stuff, and we're going to use some stuff to figure out what the a, omega, or phi is if necessary. And then finally, part C, they want to say what is the position of the cone at x equal t, at x of, or excuse me, at t equals 1.00 milliseconds. So x of 1.00 milliseconds is equal to question mark. Solution involves us understanding that x of t is supposed to be a cosine omega t plus phi, that v of t is going to be negative omega a sine omega t plus phi. Notice how omega and phi and a appear in x as well as v as well as a. And a of t is negative omega squared a cosine omega t plus phi. So that's really what we need to know here. We do know the frequency is f, so that can give us a way to calculate omega. So immediately I'm going to say a omega is equal to 2 pi times f, which equals 2 times 3.14159 times 262 hertz. And remember that 2 pi just converts cycles to radians. So we're going to say 2 times 3.14159 times 262. And this gives me 1646. And we only had 3 sig figs, so I'm going to take one more. That'll be zero point 0.2. And that is in radians per second. And technically, we only had 3 sig figs, so really the 6 and the 2 are not sig figs. But we now have that. We have omega. What we don't have though is phi. We do have A. A is 1.5 times 10 to the negative fourth meters. But what we do have is at t equals 0, x is A. So at t equals 0, x is equal to A, that means A is equal to A cosine omega times 0 plus phi. Now, omega times 0 is just 0, so what we're finding out is that cosine of phi must be equal to 1. And that means, because we know what the graph of cosine looks like, let me draw that for you real quick. Here's t, here's cosine omega t, say. And what we'd see is it looks like this, right? And that tells you, of course, that, oops, that tells you that when t is 0, we get cosine omega t equals 1. But it also tells you that if t was 2 pi, we'd get it as well. So we could let phi be 0 or 2 pi, or if you go back in time, you can see that it would be the same thing at negative 2 pi. It would also be the same thing at 4 pi, and so on and so forth. But the simplest one is we're going to say let phi equal to, in this case, 0. So now we can say that x of t is equal to 1.5 times 10 to the negative fourth meters times cosine. Now we calculated this was 1646.2 radians per second times t, like that. So this is actually our x as a function of time. Anybody have any questions on that? And of course, t would be measured in seconds. We got all the other units written there, so that should be good. Now for part B, we want to know v of t. And we could take the derivative of this, and that would give us v of t, but we can also just use the formula that we know. Either one's completely acceptable. So let's do part B. V of t is equal to negative omega a. In this case, it's going to be sine of omega t plus phi. We've already figured out what omega and phi and a are, and omega for that matter. Or I did say omega already. So we're just going to plug this in and say it's negative. In this case, we're going to take the omega, which is 1646, and we're going to multiply it by a. So the 1646.2 times 1.5 times 10 to the negative 4. That gives me 0.2469 meters per second. Because remember, the omega is radians per second and the A is in meters, and the radians can be dropped. So instead of having radians times meters per second, you just call it meters per second. And then we have times the sine of 1646.2 radians per second times t, and that is our velocity as a function of time. Everybody follow how I did that? Any questions on that one? Okay, the next part is we want a of t. So c A of t is equal to negative omega squared A times cosine omega t plus phi. So we can do just like we did again last time, but we got the negative. Now this time we're going to take the 0.2469, which is omega A, and just multiply that by omega. So 0.2469 multiplied by 1646.2 gives me 406.5. So I'm going to say 406.5, and that is meters per second every second. Now that's times the cosine of 1646.2 radians per second times t, and that is our acceleration as a function of time. Any questions on that? And then finally, for part C, they want to know x of 1 millisecond. So what they're really trying to make sure you do here is realize that, hey, when we're doing this, we're going to have our calculator in radian mode. So let me exhibit what that answer would be. So x of 1.00 milliseconds is equal to 1.5 times 10 to the negative fourth meters times cosine of 1646.2 radians per second times 1.00 times 10 to the negative third seconds, like that. So what I'm going to do is I'm going to put my calculator in radian mode. Uh, Menu. Whoa, don't want that. Uh, Thought there was an easier way to do it, but I'm not seeing it right now. Okay, well, I'm just going to convert it so that'll work. What I'm going to do is say 1646.2 times 1 times 10 to the negative 3. Now that is actually in radians. If I would like to, or if I'd like to calculate that in degrees, I could divide it by pi and multiply by 180. So that's what I'm going to do rather than put my calculator in radian mode. So this is a useful workaround for me to teach you about, even though I should really just put my calculator in radian mode. But I just bought this new calculator and it might take me a little while to figure out. I think it's pretty straightforward, but I don't want to do that in real time in class. So what I'm going to do is take this 1.6462 and I'm going to multiply it by 180. That's 296.316. Now I'm going to divide that by pi, 3.14159. That gives me 94.32. Now I'm going to take the cosine of that. So I get this cosine gives me negative 0.075333. And actually that should round to 5334. And then that times 1.5 times 10 to the negative fourth gives me ultimately 1.13, negative 1.13. Oop. Oh, it should be positive because there's a negative out in front of it anyways. Oh, no, there's not a negative out in front of it. This is the x of t. So this is negative 1.13 times 10 to the negative 1, 2, 3, 4, 5 meters is x of 1.00 millisecond. Now, if I did this correctly, that should be the right answer. Yes, your book has 1.2 times 10 to the negative fifth. I carried more sig figs, and that's probably why. So, any questions on that? All right. Well, that's the big thing about this is being able to fill this stuff in. Just as another example, let's do example 14.8. I'm going to talk to you a little bit about energy after that, and then if we have time, I'll give you what's important about chapter 15. The main thing to know for chapter 15, by the way, is that we're not going to use x equals a cosine omega t. I'm going to do this right here just to show it to you. So, chapter 15, x is going to be a cosine kx minus omega t. And you can put a plus phi on there or not, doesn't really matter. Uh, I usually do, but for some reason your book doesn't. So I'll put it right here. And that is what we call a right traveling wave. If we had kx plus omega t plus phi, that would be a left traveling wave. So that's the main thing that I need you to understand for the wave equation in chapter 15 is instead of having omega t as the argument, you're going to have kx, where k is what we call the wave number. So k is 2 pi over the wavelength, just like omega is 2 pi over the period. Okay. And we also know, for instance, that V is equal to frequency times wavelength, and that gives you a relationship between the F and the lambda. So those are the key things you got to know about chapter 15. That alone should be really sufficient, long as you've done some of the examples. But just to make sure, in case we don't get anything covered, you can at least do that. Let's go on now to example 14.8. Anybody have any questions on what we're doing so far? So this one's called spring calculations. It says a spring stretches 0.150 meters when a 0.300 kilogram mass is gently suspended from it, as in figure 14-3b. The spring is then set up horizontally with with point 0.3 or with the 0.300 kilogram mass resting on a frictionless table, as in figure 14.2. The mass is pulled so that the spring is stretched 1.00 meters from the equilibrium point and released from rest. Determine A, the spring stiffness constant K, and the angular frequency omega. B, the amplitude of the horizontal oscillation, which we call A. C, the magnitude of the maximum velocity, V max. D, the magnitude of the maximum acceleration, A max of the mass. C, the period t and frequency f. F, the displacement x as a function of time. And G, the velocity at t equals 0.150 seconds. So that's what we're trying to calculate. I need to write down what we've been given. We were given that the spring stretches x equals 0.150 meters when the mass hanging is 0.300 kilograms. Now that mass is going to stay, so I don't need to write it again. But they said the mass is pulled so that the spring is stretched to 0.100 meters from the equilibrium point and rest and released from rest. So what that tells us is V of 0 is equal to 0 meters per second, because they said that it was released from rest. And that also tells us that x of 0, which means the x at 0 seconds, is in fact 0.100. And since it was stretched, we're going to take that as a positive. Positive implies stretched, because that's the way I sort of set it up. And of course, if the negative, that would be compressed. The main thing is that we need to understand that stretch means the positive direction. Now, A, the spring stiffness is what they want to know. K equals, and they also want to know omega equals. For part B, they want to know the amplitude of oscillation. A equals question mark. Part C, they want to know the magnitude of the maximum velocity, so V max. Part D, they want to know A max. And all these are asking for the magnitude, so I don't have to include any negatives or any weird stuff like that. In part E, they want to know the period and frequency, T equals question mark, and the regular frequency measured in hertz is question mark as well. And then F, they want us to go ahead and give X as a function of T. And then part G, they want to know V of 0.150 seconds. So that's what we're trying to do. I'm going to skip writing the solution section. I'm just going to go ahead and start computing it. What we know for part A is F is equal to K times X. So K is equal to F over X, which F in this case is going to be 0.300 kilograms times 9.80 meters per second every second. And then all of that is going to be divided by the stretch, which is 0.150 meters. And if I take the point 0.3 times 9.8, that gives me 3 sig figs. And now I'm going to divide that by 0.150, which is another 3 sig figs. This gives me 19.60 newtons per meter is equal to K. So I've got that. But we also want to know omega. And of course, omega is the square root of K over M. So that's going to be the square root of 19.60 newtons per meter divided by 0.300 kilograms. So 19.6 divided by zero point 0.3, that's 3 sig figs again. So I have the square root of 65.333. The square root of 65.333 is 8.0829. And that is radians per second is equal to omega. And that's with 2 extra digits that aren't significant. So now I have the omega and the K. So part A is done. Part B, they want to know the amplitude. Now, what they told us is it was stretched and then released. Since it was stretched and released, that means the maximum it would ever get is that far away because it's going to go through, and when it reaches equilibrium, all the energy switched from potential energy, 1/2 kx squared was what it had when it was stretched out, with x being a, the amplitude. And then when it gets to the equilibrium point, all the energy is kinetic, 1/2 mv squared, where v is equal to v max. And then it goes back the other way, and it has to be equal to 1/2 kx squared, where x is equal to a again. So a really is the initial stretching amount. So we can go here and say b, a equals 0.100 meters. Now, if I had said that it was stretched 0.100 meters and then given a push to the left or given a push to the right, then that would not be the amplitude. We'd have to figure out what the amplitude is, and we could do that using energy methods or whatever by calculating the kinetic energy it had when it left, in addition to the potential energy it had when it left. Add those two together, that's the total energy. That total energy is 1/2 kx squared plus 1/2 mv squared. And at any time that you know x, you can then find v by just setting an equal, that whole equation equal to the e that you calculated from the initial position. So that's what you could do. In this case, we were lucky in that they stretched it and then released it. They didn't stretch it and then throw it further towards the stretching direction, nor did they stretch it and then give it a push towards the compression direction. If they'd done either one of those, then the 0.100 meters would not have been the amplitude. Now we can move on to part C. Oops. Part C says we want to know Vmax, and we know Vmax is equal to omega A. And we've already figured out that omega is 8.0829 and that A is zero point 0.1. So we're going to immediately say that this is 0.80829. We only have three sig figs, so the 0.808 is all that stays, and this would be in meters per second. Any questions with that part? Now we can do part D. Part D is where they want to know A max, and A max is omega squared A, which is also omega times V max. So I can go ahead and write 8.0829, and that is radians per second times 0.80829 meters per second, and that'll give me my A max. So I'm going to say times 0.80829. And that gives me 6.5333 meters per second, and that's our Amax. Of course, I also did carry some extra sig figs, so I should go ahead and underline that. But that should make sense. Anybody have any questions on that one? Okay, now we want the period and the frequency. So for part E, all we have to remember is omega is equal to 2 pi f, so that f is equal to omega over 2 pi. And omega we found was 8.0829. If I divide that by parentheses 2 times 3.14159, close parentheses, that gives me 1.2864. And that's in hertz. So my frequency is 1.29 hertz. And the period, of course, is just 1 over that. And if I take and say 1 divided by answer, gives me 0.77734 seconds, but the 3 and the 4 are extra digits, not significant digits. Okay, so now I figured out the frequency and the period, and really we're just left with part F and part G now. So X of t, we've got essentially everything we need to know, except we've got to sort of figure out exactly what phi would be. So this is where we're going to start to show you how to relate an initial condition. So what we know is x of 0 is equal to 0.100 meters. That means 0.100 meters is equal to A, which we already figured out was 0.100 meters times cosine. Now, omega times t in this case would be 0, so we'd say 8.0829 times 0 plus phi, like this. And what we'd see is in this case, phi should really be either 0 or 2 pi or something like that. So we can now say that phi is equal to 0, and that means that x of t is equal to 0.100 meters times cosine of 8.0829 radians per second times t, like that. And that is our x as a function of time. just by using the initial condition again. Now for part G, they want to know what V of 0.150 seconds is, and we can either take the derivative of this and then plug in that T, or we can just write it out. I'm going to just write it out. So G V of 1.5 or 0.150 seconds is equal to remember, V of t is negative omega a times the sine. So I'm going to say negative omega, which is 8.0829 radians per second, times a, which is 0.100 meters, times not sine, but cosine, and then 8.0829 radians per second. The 2 and the 9 are not sig figs times 0.150 seconds. Again, we've got to put this in radian mode or it won't work. So I haven't yet figured out how to put mine in radian mode, even though it should have been pretty straightforward. Nope, still nothing jumping out at me. So I guess I'll just press on and do like I was doing before. So I'm going to take 8.0829 times 0.150. That's in radians. I'm going to multiply that by 180, and I'm going to divide that by 2 pi, or excuse me, by pi. Divide that by 3.14159. That gives me 69.467 degrees. I'm going to take the sine of that. That gives me 0.9367647. 0.93647 is the sine. I'm going to multiply that times zero point 0.1 times 8.0829 and then times negative 1. And all of this gives me negative 0.75694. And that is in meters per second is V of 0.150 seconds. Again, it should be a lot easier for you because you've had your calculator a long time and know immediately how to put it in radian mode, but that's it. Anybody have any questions on that? All right. Now, in the example 14.9, they're doing a little bit more difficult than 14.8 in that they're really requiring you to use the initial conditions, and that's something you need to see even more so than you need to see chapter 15. So I'm going to press on. We only got sort of 15 minutes left. I'm sorry I didn't give you a break, but that's sort of all we can do. So let's go on to example 14.9. And what example 14.9 says is spring is started with a push. Suppose the spring of example 14.8 is compressed to 0.100 meters from equilibrium. Then it says parentheses x0 equals negative 0.100 meters. That's what I was telling you about earlier. Close parentheses. And they get and given a shove to create initial velocity in the positive x direction of 0.400 meters per second. Determine A, the phase angle, B, the amplitude, C, the displacement, X is a function of time. So what we know is x of 0, which we also call x sub 0, is negative 0.100 meters. That's because they told us it's compressed. Suppose the spring of 14, example 14.8, is compressed to 0.100 meters. That means it has to be a negative and is given a shove to create an initial velocity in the positive x direction. So we're saying V of 0, which we also call V0, is equal to positive 0.400 meters per second. So that's what the V0 is. Now what they want to know is for part A, they want to know the phase angle. For part B, they want to know the amplitude. For part C, they want to know the displacement x as a function of time. And that's it. So let's move on and see what we have here. So what we have is x of 0 is equal to negative 0.100 meters, and I'm using x equals a times cosine omega t plus phi. So I'm going to say this is equal to a, which we actually already figured out. Oh, actually, no, we have to figure it out for this one, but it's still the same spring. So we know the omega can be fine, but we don't know what the a is going to be. So I'll put the a here and then cosine. And this is the case where we can assume we know the omega, which is 8.8, no, 8.0829. 8.0829 radians per second times t. Oh, this is at t equals 0, so I don't want to write times t. I want to write times 0 seconds and then plus 5, and I'll put it in square brackets because it's a little more complex. Now, what we have is negative 0.100 meters is equal to a times the cosine of phi. That's basically all we got. Now, the other thing we have is v of 0 is equal to positive 4 point, or 0, excuse me, positive 0.400 meters per second. That's equal to negative omega, which is 8.0829 radians per second times a, which we have right there. Now, remember when we get to the v, we're taking the derivative, so it's now the sine function, and it's 8.0829 radians per second times 0 seconds plus phi, like that. Okay. Now this can be rewritten as positive 0.400 equals negative 8.0829a sine phi. And this might not look that helpful, but we can take this and call it equation 1, take this and call it equation 2, and what we can do is divide 2 by 1. So if I divide 2 by 1, I get 0.400 meters per second divided by negative 0.100 meters is equal to negative 8.0829 radians per second times a times the sine of phi divided by a times the cosine of phi. Now, what you can see by doing this is the a's cancel out and the sine over cosine is just tangent. So zero point 0.4 divided by negative zero point 0.1 is negative 4. So I can now say negative 4.00 seconds to the negative 1 power is equal to negative 8.0829 radians per second times the tangent of phi. So phi is equal to the inverse tangent of. Now again, this is a case where I need it in radians, but it's going to spit it out in degrees, and I'll just have to convert it. So the inverse tangent is going to be negative 4.00 seconds to the negative 1 divided by negative 8.0829 radians per second, which is seconds to the negative 1. So you really get no units inside the argument, but I'll take tangent inverse of zero point 0.4 divided by 8.0829. The negatives cancel out. And I got 2.69. Let me check real quick with that. Shift tangent inverse of 0.4 divided by 8.0829. Oh, glad I did that. It's 2.833. That's 2.8331. And that technically should be degrees, but I need to convert that to radians. So phi is equal to, I could say times 180 degrees in the bottom is equal to pi radians in the top. So I'll say times 3.14159 and then divide that by 180. And that gives me 0.049447 radians is the phase angle. And that is consistent with what your book has. So now that we have that, we can go ahead and write out exactly what x of t is. So x of t, all of a sudden my iPad started doing stupid stuff again. So x of t should be equal to, oh, we still got to figure out a, sorry about that. So now that we have phi, we can plug this back into, let's say, equation one. So equation one is going to say, negative 0.100 meters is equal to A times the cosine of, I'm going to put it back in degrees because I'm having my calculator issues, 2.8331. That 3 and that 1 were not sig figs like that. So this should allow me to figure out what A is. I'm going to say negative 0.100 divided by cosine parentheses 2.8331 close parentheses gives me negative 0.10012, and that comes out in meters. So I can now say x of t is equal to negative 0.10012 meters. Notice it's really, really close. But in order for me to show that it's different, I have to carry extra digits times cosine of 8.0829 radians per second times t plus 0.049477 radians, like that. And that's the function. Anybody have any questions there? Did I even? Oh, I did figure out phi. I did figure out A. So here's phi, and here's A. So that's basically it. Anybody have any questions on that? Uh, that's everything should be roughly. Oh, wait a second here. Yeah, that was fine. Cosine phi. If I'd done it maybe with equation two, I might got more sig figs. They're differing on me with regards to my A, but that's the process I went through is fine, so I don't have a problem with that. Anybody have any questions on this? All right, so I'm going to toss any chapter 15. So I can't afford the time to make up a whole nother practice test for the final. So just realize whenever you hit a chapter 15 question, you can sort of do your best to answer it. But if it appears on the final, it would only be as an extra credit. It wouldn't be as anything that's going to count against you. So keep that in mind. But the online test, I don't mind doing a little bit of that, but again, that one's an extra credit test anyway, so I don't mind changing it. I'm not gonna I shouldn't say I'm not. I don't mind changing. I'm not going to change it, so we'll have to keep that with chapter 15 just because I already made it. But again, if I look at it and I see chapter 15 is causing problems, I'll probably just give you the extra credit. So if you get something other than 100 on the last face-to-face test, or excuse me, the last online test, and it's because you missed something from chapter 15, let me know, and I'll at least go in and give you the points. I'll look at your highest one and see what I can do to give you the points. That's going to take a little bit more grading, but as long as you get it done pretty soon, I can get that done. So you guys have a good one. Thank you for coming, everybody. Again, chapter 15 is not going to be included just because I didn't have enough time, but I think these problems were really good to work on with regard to chapter 14. So I'll try to limit my chapter 14 problems to just these types of problems when I make the final. So I am proctoring a final tomorrow at noon, so feel free if anybody wants to, you can contact me and I can give you a Zoom number. If you want to take your final tomorrow at noon, you can. But you need to let me know tonight. Other than that, go ahead and chat me your first and last name and let me know whether you're from a synchronous or not. And have a good evening. Thank you, Ely. Eli. Ellie. Uh, Let me check that real quick, David, if you're still here. Looks like you are. Let's see. Students. I want classes, student forms, college catalog, tuition. Nope, not that. Uh, registrar, parents. That's not that. Looking for it. I used to be able to easily find a way to look at the course offerings, but I'm not seeing the link right now, so that's aggravating me. Mm, student form. Oh, class search. There it is. Hold this up real quick. PHY 242. Hmm. It is still showing summer. That's not helpful. I need a change term. There you are. Fall semester. PHY 242. Search. Uh, okay, so we have a DO1C and a D01B. Uh, they're on their face-to-face classes. I do have an online class, but it looks like we're only going to have, to date, it looks like we're only going to have a face-to-face lab, but I'm trying to check on that. Let's see. Why is it not showing us? Let's double check here, see what it tells me. The NO2B, yes, the NO2B is just a face-to-face lab, Monday, 9:30 a.m. to 12:20 p.m. So yeah, it looks like we're still not scheduled for that. I'll let you know, David, if I find out anything more. Hopefully we can get something done on that. But anyways, have a good one, everybody. Bye bye. Stop sharing.